It's time to take our model on a road trip. One really famous quotation about models says this: all models are wrong, but some are useful. And it's an interesting quotation because it tells us, it gives us probably a healthy sense of balance about how to trust in a model. A model is what it suggests. It's a version of reality. It tries to generalize from the particulars that we've looked at to allow us to take it and apply it to a variety of different locations. The model will never be perfect, and particularly in science where things evolve all the time, that's what science is. The model is never the final word. So what has been happening, I suppose, since the model of plate tectonics that we've been exploring has emerged is that the investigations and the papers that scientists have been writing have been taking this and exploring it in a whole variety of different contexts. And a lot of the papers that I've been reading have gone into really particular detail of particular locations. It's part of what makes finding out about this topic so difficult, because a lot of the model itself is just assumed in these papers in terms of the knowledge and awareness that the reader will have, and they then take these models and explore them. So hopefully now that you've got an idea of what that model is, it frees you up to do a little bit of what I'm going to demo here. I'm just going to guide us through a few different road trips where we'll take the model and batter around a little bit and see how well it copes and survives with the journey. But it might also free you up to go and do a little bit of your own investigation in terms of some of the tectonics papers that are out there. It might enable you better to be able to then go and delve into that incredible world yourself. So, and here's our other model that we've been looking at, the mental model, our schema that we've been seeking to construct on the way through this expanding evidence base, the evolving theory. We started with the continental evidence through Holmes and his first hints of convection currents, back into the seafloor evidence, down via Hess into convection currents. But then we discovered late 60s, early 70s that convection includes the plates and is mostly driven by the plates. In the last video, we went on then to take a look at seismic tomography and the mantle evidence that is there to support this theory of slab pull and ridge push. And remember again our quotation from Konrad Lorenz: truth in science is defined as the working hypothesis best suited to open the way for the next and better one. So we're going to look here to see the extent to which this model actually works in the real world. And like any to what extent question, we're going to discover the answer is to a certain extent. Where it lies in that spectrum, we'll decide when we get towards the end. Here's a quick reminder of our model again. What we're going to be looking for here is slab pull is the main driver, this negative buoyancy of the cooling from the top, dragging the plates down with it, creating the tension, and the ridge push, which as the material slides off, it pushes it away. This is what we want to be able to see and investigate in the real world. And the first place that we're going to go to is probably the classic place, which is the best place to give this a test run. So if we're going out in our test run, this is us taking it onto the perfect road, because this is going to show it to its best. And we're going to zoom in here to the South Pacific, going from a cross section here from New Zealand and the Tonga Trench through the East Pacific Rise over to the Chile Trench here in South America. So let's zoom in a little bit closer. So the first question that I would have for you is, could you draw a mental cross section of that transect in the blue dotted line? What would it look like? What are you expecting to see? Shall we pull up the seismic tomography scans from here and see what they actually show? Is that what you were expecting? Can you see the slabs? There they are. And there is the Pacific rise. Now, as I said last time, the resolution of seismic tomography is not fine-grained enough for us to be able to resolve the rising plumes here. Sorry, I shouldn't say plumes. The rising passive convection underneath the ridge. So this is not something that you should expect to see in the seismic tomography scans, but certainly there is this descending slab there and there. So it does very much seem like this is very similar and akin to our model. We'll have the seafloor spreading there, the age of the rock getting older in a reasonably symmetrical pattern with slabs pulling it down here at either side. That's exactly what you would expect to see. So it looks like our model has good explanatory power in the South Pacific. Let's add another little chunk along here though. Let's add over here and head towards the Atlantic Ocean. What would you expect to see there? What would the cross section look like here? More like this, isn't it? What we have here is most definitely our ridge push taking place. But this is where we start to see that this is a little bit different from our model. There isn't a destructive plate margin there. This is a passive margin here where the ocean lithosphere meets the continental. There's a passive margin here. There is no subduction here, at least presently there's not. So what we're seeing here is that the main force that's driving this is your ridge push. Now, we'll begin to see a little bit of evidence here, I think, that your slab pull is the main driver when we look at the speed or the rates of movement here in the two oceans. Which of them is moving at a faster rate? Can you tell? Well, if you look at these isolines here showing the age of the seafloor, you can see that they're much more widely spaced here, implying that the seafloor here is moving at a faster rate, whereas they're much closer together here, implying the seafloor is moving at a slower rate. And if we pull some figures in, the South Pacific Ocean is moving at rates of around about 10 centimetres per year. The South Atlantic is around about 2.5 centimetres per year. So the plate which doesn't have the slab pull, that only has the ridge push, is moving at a slower rate. The plates that have ridge push and slab pull are moving at a faster rate. Now, it does raise interesting questions. I wonder, are you ahead of me? Are you asking the question, well, where's the tension coming from in the mid-Atlantic? Well, it's a good question. This is one of the areas where the model is a little bit more limited. So there are a couple of destructive margins in the western part of the Atlantic, around about the Caribbean and the South Sandwich Islands. There's a little bit of slab pull taking place. And maybe whenever the continents were breaking up, when Pangaea was breaking up, it got started by this process aided by some of the hot spots that are found through the Atlantic Ocean. But we're already beginning to see where this model perhaps doesn't have the final answer, but we wouldn't expect it to. But we're certainly seeing that where we have the classic one, we've got the ridge here, ridge push, slab pull is moving faster than the system where you've just got the ridge push. So it seems to confirm that the slab pull is one of the major drivers of plate motion. Now, there is another interesting thing that you can do in the road tests of this. I actually have done this with my sixth formers. It's a really, really interesting task. And with the right scaffolding, you can guide them towards it. Let's look again at the Atlantic Ocean. In the Atlantic Ocean here, we have got the mid-ocean ridge in the middle of the ocean. The distances here and here are about the same, and the symmetry here and here are equivalent. So in this sense, this is much more like our model. It is the symmetry that we're expecting because this process is being pushed out from the center here at the ridge. Whereas we come over here and we see that the East Pacific rise is certainly not in the middle of the Pacific. It would probably need to be here for it to be in the middle of the Pacific. So this, the western part is much, much longer than the eastern part. So there is a kind of a symmetry in the speed, but you have much, much older plate here than you do here. Now there's an interesting question, problem-solving question for your sixth formers. Why is that? Any thoughts? Why is the East Pacific rise not in the middle of the East Pacific? And of course the answer relates to what's happening here in the South Atlantic, because the South Atlantic has only been opening up for probably around about the last 70-80 million years. Whenever Pangaea was still a supercontinent, when South America was still connected to Africa, the Pacific Ocean would have been bigger and the East Pacific rise would have been in the middle of it. But since then, we've had South America moving closer and closer and closer and gobbling up more and more and more of this plate, the Nazca plate. So therefore, as a consequence, the East Pacific rise is no longer in the middle of the East Pacific because South America is heading that way and gobbling it up. Let's look at this in diagrammatic form. I tried my best to try and recreate some of this, so there are a number of weaknesses in this diagram, but go with it. Hopefully it'll indicate to you a rough idea of what I'm trying to do here. So here we have the situation 200 million years ago, whenever Pangaea was a supercontinent, and the East Pacific rise, and the size of the Pacific Ocean being more or less the same on either side. But then we start to get the split up of the supercontinent, and we start to get South America moving here as the Atlantic Ocean begins to form. And you can see here that while this is being created, seafloor is being created here, because this plate is now moving west, it is starting to eat into the Pacific plate here, or the Nazca plate as we've come to know it. There it is, it's moving over. And then if we bring it into its present day position, as the Atlantic continues to spread by ridge push, then it means that this trench is rolling back closer and closer and closer to the East Pacific rise. The Nazca plate here is getting smaller and smaller and smaller. So that would lead me to a question. Does that mean that ultimately the Nazca plate is going to disappear entirely? Will South America eventually come and gobble up the East Pacific rise? Let's explore that, shall we? Now for that, I'm going to come into a GIS map. It's going to help us to explore this a little bit further. And I thought I would just take a few moments now to create this GIS map with you. I'm going to go through this pretty quickly, but you can pause the video if you want to see exactly how I'm going to go about doing this. The first thing that I want to do is to change the base map to show us the seafloor, the oceans. It gives us a little bit more of a sense of the topography. So here we have our East Pacific rise running up there. There is the Tonga Trench, there's the Peru Chile Trench, and there is the Mid-Atlantic Ridge. So this area that we've just been looking at. And here comes this rise up here until something happens up here in North America. Right, so I want to add on the plate boundaries. So I'm going to come to add and search for layers, and I want to look in the ArcGIS online content. And I'm going to type in here plate boundaries. Searched for that before, so it's already in there. And I just click the little plus here to add it on, and the layer will appear. Those are all the different plate boundaries. Now, whenever it first appears, it just shows the plate boundaries themselves. I want to show the different types, so I'm going to come into the content, these little shapes here. I'm going to click on this to change the style, and I'm going to click on type. So this is now showing the different types of plate margins for me. I'm going to click done, and there I have the different types. So if we zoom down in here to the area that we've just been looking at, there's the Tonga Trench with the convergent or destructive plate margin. We come over here. Here's the East Pacific Rise. Here we have the Nazca Plate, South America, and into the Atlantic Ocean and the Mid-Atlantic Ridge. So our question was, is South America eventually going to gobble up the East Pacific Rise? Well, the answer to that is that we don't need actually just to speculate, because North America is considerably further west than South America is. Probably more so than we reckon sometimes, because there's Florida, and Florida actually corresponds almost with the west coast of South America. So if it is much, much further over to the west, then that means that we're kind of getting a little bit of a glimpse into the future of where South America might be, just by simply looking at North America. And if we come in here, let's follow up the East Pacific Rise. Here we go. We're following this up here past Central America, and then we come into Baja California, this peninsula here, and the Gulf of California. What we're noticing here is that this is a linear sea that is just beginning to form, and then we've got this massive big transform fault, this conservative margin through most of California, and then we have a tiny, tiny little plate, the Juan de Fuca plate here, which is where us back again to our spreading margin. Here we have a ridge here, and a destructive plate margin here at Washington State. Can you picture what's happened here? So basically what has happened is that North America has crashed into that constructive plate margin, that divergent margin. It has consumed it and ridden over the top of it. And now we have this constructive plate margin here and this transform or conservative margin here meeting this tiny, tiny little remnant of what was the Eastern Pacific, the Nazca Plate. So what's going to happen in the future? It's highly likely. Sorry, that should have called that the Juan de Fuca Plate. What's going to happen in the future? It's highly likely that the Nazca Plate will suffer the fate of the Juan de Fuca Plate as South America continues to move across this way, as it is pushed here by the ridge push. Okay, let's do a little bit of science here, shall we? Because if our theory is right, we should be able to see something under North America. Because what it has done has kind of consumed that destructive plate margin as well. It's no longer here in California, but it was there in the not too distant past. So we should be able to see something under North America, shouldn't we? Are you ahead of me here? Do you know where we're going? Well, we're going to go back into the Atlas of the Underworld, of course, for this. So let's go and have a little bit of an explore. So I'll zoom out a little bit here. First of all, I'm going to bring us back down here to South America just to get a frame of reference for what we're expecting in locations like this. So at the moment, the South American plate is moving over the Nazca Plate here. The subduction zone is occurring along the trench here. And what are we seeing down below? We're seeing the subducting slab going in underneath South America. That's exactly what we'd expect to see, right? Let's move up a little bit. Let's stop off in Central America, Guatemala. Here we have the destructive plate margin, the convergence zone here. So we should have subduction under Central America. Do we have that? Yes, we do. There is the slab going down into the lower mantle down to the core mantle boundary. We are seeing exactly what we should expect to see. Now let's come up to this bit here. We're into Washington and Oregon, and we're at the location of Mount Rainier, Mount St. Helens, places like that. So should we see something of a slab coming down there? Let's move this over a little bit. And yeah, just about. There it is there, coming down and underneath. But what would happen if we drew something from here, from California, all the way across South America, or North America? Okay, if our theory is right, North America has moved all the way over the ridge here, and there's no longer a destructive plate margin at this location at the moment. But relatively recently, geologically speaking anyway, there would have been. So what are we going to see under North America? Look at what we have under North America. There's our transect. We have got the former slab. Now, it's not really attached there anymore. You can see that, right? It's detached, but it's still there. Remember, we learned before that destructive plate margin probably isn't the best title for this plate type because the plates aren't destroyed. They're relatively cold enough compared to the rest of the mantle that they seem to maintain themselves, at least to the mantle transition zone, and very often all the way further on down. And here we see evidence of an ancient plate from a plate margin that doesn't even exist anymore. And here we can find it, because we're doing some science. This is called the Farallon plate. And it was the name of the plate that would have been the equivalent to the Nazca plate, that before North America moved over here and consumed it, there was that destructive or convergent margin there, and the Farallon plate was plunging down into the mantle below. Now it's going to take maybe a few more 100 million years for that plate in its entirety to reach the core mantle boundary. So for quite some time yet, you're going to have this feature recognizable through seismic tomography, all going on down and underneath there. And that's the kind of thing you can do as you road test this. And again, that's what I do with my sixth formers. Now, this pushes them right to the edge, but if I've taught this well enough to them on the way through and they're properly scaffolded, these are amazing moments for them to go, oh, wow, yeah, I mean, I can go and do science. I can come up with a hypothesis and I can go and gather some data from the Atlas of the Underworld and I can do science. Wow. Okay, let's come to another part of the world to do a little bit of a road test here. Can you recognize where we're at? We have come now to the Indian Ocean. Here is Africa, here's India, here's Australia and Southeast Asian islands. Now, before I go any further, I wonder, can you kind of decode what you're looking at there? Can you recognize any of the patterns that might be observable here? So the first thing I'm going to do is kind of turn this around a little bit, reorientate this and maybe simplify it down a little bit to let us see a bit better what we're looking at in the tectonic context. What we seem to have here is a divergent or constructive plate margin. Up here we have our island arc of the destructive or convergent plate margin. And up here we have the convergent plate margin or collision zone as India goes into the Tibetan Plateau. So based on our model, what are the tectonic processes that are going on here that are moving these plates? What do you think? Well, we've definitely got evidence here of the slab pool because we've got the subduction zone. So the Indian plate here is subducting down here under the Sunda Trench. So we're definitely getting a slab pool here. This is a divergent plate margin, so we're going to get a ridge push here. So we're definitely getting both of the forces in operation at this point, but we do have an interesting little addendum to this, because India, which used to be completely separate, has now crashed in, collided with the rest of Asia to create the Himalayas and the Tibetan Plateau. Okay. Let's take a wee look at some of the interesting things that are happening here, because we have to do a few little tweaks to our model to fully understand this. I'm going to look at two earthquakes that occurred here, one of which is extremely famous, you will know, and the other one is a lot less famous. The first one is the Boxing Day tsunami in 2004. It was a magnitude 9.1, one of the biggest earthquakes in the world. It was a subduction zone earthquake, a megathrust earthquake, and the subduction zone is the subducting plate came down, the overriding plate eventually sprung back up again, and that lifted the water up and created that devastating tsunami that killed something in the region of 230,000 people. Absolutely devastating. It's the kind of earthquake that you've probably taught, and it's an earthquake triggering system that isn't going to be hugely unfamiliar to you, the springing up of the overriding plate. But let's fast forward to 2012, whenever there was another massive earthquake just very, very close to the epicenter of the Boxing Day tsunami. This was a massive earthquake too, magnitude 8.7. 10 people killed. It's probably the reason why it's a lot less famous, isn't it? So how does a very, very big earthquake, very close to the Boxing Day tsunami, produce a different earthquake outcome? And the reason for that is because what this location is in the middle of the plate. You can see that there's a pink line on there. We're going to explore what that means in a moment. But this is an intra-plate. This is an interplate earthquake between two plates. This is intra within a plate. In fact, this is by far the largest intra-plate earthquake in recorded history. Normally magnitude 8 earthquakes or above are associated with these subduction zones where you get the megathrust earthquakes. So what's the mechanism at work here? Let's see if we can put this all together. Because remember, we're getting the ridge push from here, we're getting the slab pull from here, and India is colliding into Asia at this point. Now, what do you think this is going to do to the speed of movement of the plate here compared to the plate here? Remember when we looked at the South Pacific where you've got slab pull occurring, it tends to move faster. So you've still got slab pull acting on this plate, but you've also got the collision here, the resistance of Asia as India moves in. So what are the rates going to be like? There they are. At this point, we're going at about 5.6 centimeters per year. Over here in India, about 3.7 centimeters per year. Now, India is still moving because you may be thinking to yourself, how does India move if it's collided? Surely that resistance is going to stop it. Well, it's going to slow it. But India is part of a massive Indian plate. Look at the length of that subduction zone here, which is giving that slab pull force. So the whole of the plate is being pulled, the whole of the plate is being pushed, this part of the plate is colliding, which is why it is continuing to move despite the resistance. Grab a drink. But the rate at which it moves, because of that resistance, is different. Now, can you picture what then must be happening in this location? In fact, certain maps will mark this on more as a zone rather than a single line. What you're getting here is a zone where you're getting a range of interesting forces operating together. They are both moving in the same direction, but they're moving at different speeds. So you can get that forces building up. And the forces that are building up then are creating the pressure and the tension which was released in these earthquakes. In fact, the The 2012 earthquake was highly complex. It activated about 4 major fault zones. Highly complicated because what is happening here is a really complicated twisting and turning and faulting of the plate itself, which ultimately, in this sense, if this one is moving faster than the other one, kind of creating this twisting and compression force here. So this is experiencing a compression force as a result of these processes that are going on. And seismologists believe that this might be the beginnings of the next destructive plate margin. It might end up initiating subduction here in order to accommodate all of these different stresses. So keep our eye on that one, or at least keep your eye on that one if you're willing to wait around for a few million years. It's interesting to see where that might go. Just a quick check of what we've been just suggesting here using the Atlas of the Underworld. If we look at a transect here from A, B, through the ridge across here to the trench, here is our subducting slab. We have evidence of it subducting all the way down. So we're getting the slab pull force operating here. What if we were to draw a transect from A in Madagascar here through to India? Now remember, this is all the same plate. This is all the Indian plate. India is only a tiny part of the Indian plate. Here we can see the evidence of the slab underneath there, showing us that there was subduction here in the past. The slab has not been destroyed. It has continued down into the lower mantle, but it has completely detached now from the plate above. In fact, it's got entrained in this higher density lower mantle, so the plate above is actually moved past it. The slab is now, if you imagine a kind of like a shape like this, there's India there, and the slab is now bent round the other way because it becomes entrained in this higher density mantle down below. Okay, now we're taking our model on a really good road test here, aren't we? And we've moved away from the simplicity of the model and taking it into these real world scenarios. As I mentioned earlier, this is very much how the papers these days, as the scientists are grappling with this, they're going into finer and finer grain detail to see if they can figure out what's going on. But let's take a look at something else to do with the Indian plate. This is not something that I've ever done with my sixth formers, and I don't know that I ever will, but I'm working again on the principle that I don't want you just simply to be butting up right to the very edge of your knowledge in this. So we're going to finish off our series of videos by having a lovely little juicy detailed exploration. We're really going to take our model on a very exciting road test here. If this was Top Gear, it would be one of those hairpin bend mountain roads in the Italian Alps that they'd be driving through. We're really going to test our model out to its fullest at this stage, because we're not just going to look at the spatial patterns of India like we've just done. We're going to take a look at the rates of movement over time, the temporal patterns, because as this graph shows, the rate of movement of the Indian plate in the last 80 million years since the breakup of Pangaea has showed considerable variability. Sometimes it speeds up, sometimes it slows down. More to the point, sometimes it speeds up faster than we would expect if the combined forces of ridge push and slab pull are the only ones in operation. We have seen from looking at the South Pacific that if you've got slab pull in operation, the plates will move faster than if you've only got ridge push operating alone like you have in the Atlantic. But combining them both together, and we typically don't get rates of movement much more than 100 millimeters per year. And yet, evidence would suggest that there is something been happening here in this Indian plate over this time period that has given it a speed boost, making it travel faster than we might otherwise expect. If you've ever played Super Mario Kart, this is kind of like going through the little speed boost whenever you are playing that game. Whee! Off you go as you go much, much faster than everybody else around you. Is there some kind of Super Mario Kart speed boost happening here that has produced this pattern? Well, let's have a look. First of all, we'll take a look here at where India has travelled since then. So this is around about 90 million years ago, and this is the breakup of Pangaea. India is moving away from Africa and Antarctica and Australia, part of the same plate as India. The Indo-Australian plate is moving north. The reason for that is we have our convergent margin here, which is going to give us our ridge or our slab pull force, and our divergent margin here, which is going to give us our ridge push force. So you're getting pushed from the south, you're getting pulled from the north, and that's just our model in operation. This is the processes that we're expecting, doing what we expect those processes to happen. India moves further north over time, but something happens around about this time that speeds it up. You can see that India has moved considerably further than Australia has at this stage. So what's happening under India that's given it that little bit of a speed boost, the Super Mario Kart effect? And again, there we can see it. It's travelled much, much further than Australia has. And remember, they're part of the same plate. You can see the plate margin developing here. And I want you to note this, because this is something that's quite significant, which I think is part of the answer. And then we're just before the collision of India here with Asia. And around about 40 million years ago, according to the graph, it slowed down. Now, part of your theory or your hypothesis for that might be that the collision here has caused it to slow down. We know that's part of it. But we're going to go and have a little analysis here to try and see if we can figure out what's going on. And this is a paper that has just been released at the time of recording. It's only out about a month, and by Pusok and Stegman, and looking at this whole speed process and trying to come up with some hypothesis as to why this might be the case. Okay, so we go back 80 million years ago. Pangaea is just beginning to break up, and India is being pushed from the south. Subduction is occurring underneath Asia, so the plate is being pulled from the north. Ridge push and slab pull operating, moving it north within the typical rates that we would expect if both of the forces are in operation. There's nothing unusual here according to our model. But then we get this speed boost, the Super Mario Kart effect, and it goes up considerably, well above what we would expect. According to the paper, they're suggesting that this is because India has moved over the reunion plume. So the mantle plume rising up below reached the bottom of India around about kind of 65, 70 million years ago or so. And that led to a massive big volcanic eruption producing flood basalt, the Deccan traps, which some people are suggesting maybe contributed to the kind of climate change factors that led to the extinction of the dinosaurs. There's some evidence of these massive big basalt eruptions taking place periodically that align with periods of significant extinction events happening. Perhaps it worked with the meteor to kill the dinosaurs. But certainly what seems to have happened here, according to this paper, is that whenever it comes up under India, the shear forces, the friction between the plume and the plate above, gave it that little bit of a boost as the mantle material, or the plume material spread out, causing it to move. And that's what gives us our boost. Because what we've now got is our ridge push, we've got our slab pull, but we've also got our plume push in operation. And that gave it that extra push, which brought the speed up to those incredible levels. But I want you to notice something that's happening here as well. Because this speeding up here is creating this compression force on this part of the plates. Let me give you an illustration for that. Imagine that you're on dinner duty in the canteen and you've got all the pupils lined up in the queue being extremely well behaved because they always are. Nobody is pushing anybody because nobody ever does. And the queue is just slowly moving forward in a very orderly fashion. Then the door to the canteen bursts open and you get an excitable bunch of students who join the end of the queue, and they come in with their enthusiasm and they nudge the end of the queue. Now the queue is moving forward, but the back of it is now nudging forward again. So you're going to get that compression in the middle of the queue. So that's very similar to what this paper is suggesting is happening here. That you're getting at this point this compression, which is putting strain and stress on these faults. Watch that, because that's going to be significant. So we've got the ridge push, we've got the slab pull, we've got the additional boost of the plume push, which pushes that speed up. Then if we look at the speed, it reaches its peak. So that's up here towards the top, and according to this paper, this is the peak of the plume push. That the force from the reunion plume is giving that speed boost to India. But notice, because of the compression here, you've got the initiation of subduction. Now this is very similar to what we think is possibly happening in the middle of the Indian-Australian plate at the moment. That 2012 earthquake is perhaps an indication of that compression, which will ultimately, potentially lead to the initiation of subduction. So watch that, that's going to be significant. Then the speed comes way, way down. Now, what do you think might be causing that drop in speed? Here we had three forces: the ridge push, the plume push, and the slab pull. India continues to move further north, and it moves away from the influence of the reunion plume. The hotspot stays put, the plate moves away. So what you're getting here is the waning of the plume push, the speed drops down. And the subduction is just beginning to initiate here, so it hasn't really picked off yet. So you get this drop. Now it's still faster than average, but it's dropping down and down and down. And then this happens. The speed goes back up again. What do you think is going to give it a little bit of a boost here? Have you any hypotheses? Let's have a look. So what has happened in this case is that the subduction that is initiated has now got well established. So you have got double subduction. Subduction here and subduction here. And of course you've got the ridge push happening as well. So you've got your three push and pull forces in operation again, which gives it that little bit of a boost of speed. Not as much as the plume did, but it's still going faster than you would typically expect. Then the speed drops down. So we're going to lose one of these subduction zones. Which subduction zone do you think we're going to lose? Well, it's this one, because this plate continues to move forward, and just as we saw with the Pacific plate and South America, the Nazca plate in particular is being consumed. So this plate ultimately will be consumed. Subduction will finish. The plate will ultimately detach, travel further down into the mantle, and will break up probably. So you're back here again just to one single force of subduction and your ridge push further to the south, which brings us then to what's been happening since then, where the speed has settled down because and become a lot lower, because now this plate has collided in and there's no longer any subduction taking place. Subduction has stopped, at least at this location. You're getting the ridge push, and you're getting the subduction around about the Sunda Trench, which is pulling it forward as well, but the rate has got down an awful lot lower at that point. Now, what a fabulous way to road test our model. We've introduced a couple of things that definitely go beyond what you would want your sixth formers to do, unless you've got a particularly gifted sixth former who's going to lap this kind of thing up. But what it does show is the essence of what I've been trying to communicate all along. This is an evolving model. It's evolving science. As more and more evidence becomes available, as we're studying these things in ever fine-grained detail, we're going to get much more subtlety and nuance of understanding. Is this hypothesis right? Don't know. But remember, science is the best current hypothesis of understanding that creates the best conditions for the next and better hypothesis to supersede it. The end? Yeah, it is the end this time. So, as wrapping up, just let me say a couple of things to finish off. David Berkovici says this: one of the major questions and mysteries about the mantle remain unsolved, and thus are ripe for discovery for future generations of earth scientists. Wouldn't it be great to think that if we were to teach plate tectonics in this way with our pupils, that we might entice some of them to think of earth science as a career, and some of them may well, in decades to come, be writing some of these papers that you might be reading as you explore and expand your own ideas. And then this quotation from Max Planck. He says this: a new scientific truth is usually not propagated in such a way as the opponents become convinced and discard their previous views. In other words, this is what a lot of the proponents of what became plate tectonics in the 20th century faced with the fixists. They were almost dogmatically stuck in their own views. They weren't interested in understanding how this theory could evolve. No, says Planck, the adversaries eventually die off, and the upcoming generation is familiarized anew with the truth. Well, let me suggest this. The last thing that we want to do is wait until all the generation of the current geography teachers has died off in order for true understanding to come through. If anything is going to get slayed, let it be those zombie ideas. Let's get rid of the zombie ideas of the convection currents in those neat little cells. Let's do science, and let's enjoy every moment of it.